Okay, I'm going to walk through the circuit of a plus or minus 15 volt dual supply. This supply is useful to me because I want to run chips that require a plus and a minus voltage. You'll often see that come up. If you just want to use batteries, it's very simple to just take two batteries, and then, for example, if I take these two batteries, these batteries are 1.2 volts. So you've got, if you connect these together, plus to minus like this, then that battery there, the whole voltage across from the top to the bottom is 1.2 times 2, which is 2.4 volts. So if I measure that, I'll measure 2.4 volts from top to bottom. Now, the point of a dual supply is we're going to say in our circuit that this point here, we're going to treat that as what's called the common. In other words, that there will be common with respect to our circuit. So it's just a name, that's all it is. All we're saying is we're going to take this voltage to be 1.2 volts above that point, and we're going to take this end to be 1.2 volts below that point. The words we use to describe that is we just say that's 1.2 minus and that's 1.2 plus. So that's really what we're talking about when we're talking about plus and minus voltage. It's plus and minus relative to the point that we've chosen. In this case, I've chosen the middle of these two batteries. If you don't want to use a battery, but you've got a chip that requires a plus and a minus voltage, in other words, the voltage below some common value, then you can build yourself a dual voltage power supply. So what I'm going to do now is I'm going to go through each of the stages. So the first stage of this dual voltage power supply is the transformer stage. The next stage, I'll talk about the rectification of that output voltage from the transformer, how we rectify it and how we get our plus and minus voltages. And then on this section here, this is the filter section, I'll explain what we end up on the other end here is a pulsating voltage and how we actually smooth that out. And then finally I'll briefly go through a regulator. You go and check out my other video on how a power supply works. A lot of this is repeated really, so I'm not going to go into detail how a regulator works. If you want to know how a regulator works in more detail, go and look at my power supply video. So here I'm just going to gloss over that, but just to give you the general view. And then once we've covered this, I'm going to show you how I actually connect up the units that make this power supply and the components, and show you how they're connected up. I'll talk about the components, why they're needed, and then at the end I'll show some photographs of the actual finished power supply and maybe a few tests to show you that it's working. If you follow this quite carefully, you can make one of these yourself. You could take a snapshot, you've got all the values. I'm going to zoom in on each of these parts so you can, and then I'm going to talk about the components on each of these parts. So let's talk about the transformer next. Okay, so now we're going to talk about how the transformer works and how that is rectified, and then finally how it's filtered through. So we're going to talk about this section, and really what we're going to do with this is take us up to the filter part, and we'll talk about the filter part as we move forwards. These two resistors here, I'm using them at the moment here just to explain how this section works, but in reality they're not there. There'll be capacitors there, but I'm just using those at the moment so you can follow what's going on here in this part of the circuit. You'll notice that I've used these large wide pipes here. The reason I'm doing that is for a visualization. I found when I was trying to understand how charges moved through wires, the visualization that helped me, and I hope it might help you too, so I'm going to use it, is to think of charges moving through pipes as all touching each other. Now each of the, you can see in here in this diagram, what I've tried to draw is lots of little circles with a little dot in the middle. Now each one of those little dots I'm representing in my mind as a charge, and the outer surface, the round circle around it, is the repulsive force. Now because all of them are the same, you may or may not know that like charges repel and opposite charges attract. So all of these charges are all of the same type, so they're all repelling. So this outer circle is supposed to represent the repulsive force. Now you can think of that as a hard surface, and now this is where the visualization makes it quite simple, is you can think of them as marbles. That hard surface is the outer layer of a hard marble, so they're all touching each other, and they all want to get away from each other basically, but they can't because they're trapped inside the copper. So with copper wire, for example, it's filled with these charges. You know, whether the copper wire's connected to an electric circuit or not, you know, it's been filled with charges since the beginning of time, you know, and all metal has, you know, and metal is one of those useful things for us, is that charges flow easily through metal, so that although they're all packed with these charges, it's easier to give them a little shove and get them all to move. Yeah. So what you can think of is, if you look at one of these pipes, is think of at one end of the pipe someone pushing a hard marble. Think of the hard marble as a charge, if you like, and that's what I'm doing here with this visualization. Push that charge into one end of that pipe, and what happens? Well, the energy you've used to push that charge into the pipe is transmitted at the same instant all the way through the pipe, because remember, all the charges are all touching each other. So at the other end of that pipe you'll find that there's another marble, a charge, that if, for example, at the other end it's an open space, then if we push the charge at one end, and of course this doesn't happen in reality because you need a complete circuit, but just for this visualization, if I was to push that charge in to that pipe, then out the other end another charge will drop out exactly the same instant, no matter how long the pipe is. So that's the idea of you think of your hand as pushing it as the voltage, if you like. So your hand is pushing that through, and that energy is transmitted at exactly the same instant as you've pushed that first marble in. So that's the idea of how energy is transmitted through a circuit. So that's all you need to really think about when you're thinking about how is energy used up. Think of it like that. You're pushing a charge in one end of a pipe, and all that energy is transmitted through all of the marbles are all touching each other, so that whole energy is transmitted all at the same instant until the one at the other end actually moves. So for example, if you switch a light switch on, the bulb could be like miles away, but you know that it'll go on almost instantly. And you might think, how could that happen? Well, that's because in that wire, all of those charges, no matter how many connections there are, you've got a line of charges all touching each other, making a complete circuit. So at the bulb end, through the filament, when you push that first charge through at the other end, when you switch the light switch on, the charges that are sitting in the filament are all being pushed through, and all being pushed through a very, very thin pipe. Now, if you push something through a very thin pipe, you're going to warm it up. So that's why you get the heat coming off the bulb when you get light. So that's the way you can think of this instant transmission of energy. So that's really a very useful visualization to understand most of electricity, really. And that's how I've always understood how these things work. So I thought I'd give you that now. So that's why I've drawn it like this. Now you can see here what I've done here. If we're looking at this, we've got these two helixes here. Now these represent the initial primary winding of that transformer and a secondary winding of the transformer. So we've got this main transformer, and the transformer is going to transform 240 volts down to, this is 36 volts from the top here to the bottom, but because we're going to place our black lead in the middle of this coil, we can actually refer to it as 18 plus here from our, what we refer to as our zero, just like in our batteries example, and minus 18 from this center point here. So minus 18 volts from this center and plus 18 volts from the center. But you could also say it's 36 volts from here to the bottom. So you've got 240 volts, this primary winding, and what we'll end up with is a step down voltage of 36 volts. Or, because we've stuck our multimeter black lead here and our plus red lead here, we can call that plus 18 volts, or we can stick our red lead at the bottom and call it minus 18 volts. So that's the idea of using the battery, is to give you that kind of visualization. So what I'm going to do now is I'm going to talk through how the charges move through this primary and what causes the secondary charges to move, and then how they move through this circuit. And then I'm hoping you'll get an understanding of how this dual voltage power supply actually works, because this section here, this transformer, understanding this transformer and understanding these diodes transmit this energy through this part of the transformer, part of the circuit, will give you the complete understanding of a dual supply. And the important thing we're going to go through is this center tap and how that relates. And that, once you understand how this center tap relates, you'll understand this all. Now, the interesting thing about this circuit is it's probably this, in terms of the parts, it's probably the simplest circuit you could imagine, because how many parts have we got here? We've got a transformer which basically consists of 2 coils of wire, one coil wrapped around another coil. We've got 4 diodes, and although I've got resistors here, like I said before, 2 capacitors. That's it. That's the whole circuit. There's nothing else to it. And of course the second winding has been tapped in the middle, and the middle is joined between the 2 capacitors here. So let's look at this primary winding to begin with. When I'm talking about these voltages, I'm talking about 1/50th of a second. So when I said to you before that there is 36 volts with reference to that being 0 volts, or that is 18 volts with reference to that being 0 volts, that is for 1/50th of a second. Remember, with an AC voltage, you've got 240 volts at this end that's swapping over, and of course that's being transformed down to this 36 volts. So one moment, 1/50th of a second, 36, we can call it 36 volts, and that with reference to that. And then the other, we can say the other 1/50th of a second, the charges are going to be flowing in the opposite direction. So then we can say that that's plus 36 and that's the 0. I hope that makes sense. Every 1/50th second, the charges will move in one direction, then they'll move in the other direction. So what we're going to talk about here is just take one direction arbitrarily, coming this way, going through this primary coil and coming out. So let's go through this now and explain what's going on. So what's happening here, we can just imagine that at a power station, there's a whole layer in one of these pipes of charges. 240 joules of energy is being used per coulomb of these marbles, if you like, is being pushed. That's how much energy. Now we can think of 1/50th of a second, they're all, let's say they're all being pushed during that time in this direction. So that's what we're going to do. So they're all being pushed, so no matter what, they're going to be pushed. So they're all pushing their neighbours, and they're going to go through this helix here, this what we call the primary winding. They're going to come out and then go back to the power station. That's going to continue to happen. They're going to go through there all the while during this 1/50th of a second. They're going to be going in that direction. The next 1/50th of a second, they're going to swap and they're going to go back. They're going to come, then they're going to come in the opposite direction. But we'll talk about that in the next sheet. Let's talk about one direction first and see what happens. So for the first 1/50th of a second, all charges are being pushed through this primary winding. Now the interesting thing, if you have 2 coils of wire next to each other, when you push charges through one coil of wire and you've got another coil of wire which we'll call the secondary close by, it will cause charges to move through the secondary. So that's important. That's the only thing you need to understand really about the transformer. So given that, charges are moving through this helix, they're all going in this direction. Now what happens is it actually produces a magnetic field. Now when the magnetic field is growing, it causes, I won't go into the details, but it causes charges to flow through any nearby wire. That's coiled wire in this case, in the secondary winding. And that will actually, the magnetic field that's grown due to this first primary will induce charges to be pushed. And in this case, we're saying that they're being pushed from the bottom of this helix all the way through out to the top. Now you can think the fact that they're being pushed, this induction, this process called induction, you can think of that as a voltage source. So now forgetting about the primary, let's just imagine that we've got a voltage source now. So this 1/50th of a second, we can think of this, because the charges are being pushed out of this secondary coil, we can refer to that as our plus. And because they're being pushed back all the way around, so this we'll go through this, and this will actually produce a complete circuit. And what will happen is, because all of these marbles are all touching in this complete circuit, as we're pushing these ones, obviously those ones are going to move at the same time. Everything moves around. It's like a complete wheel, if you like. So all the rubber of a tire of a wheel, if you move one up, all of it's going to move together. That's exactly the way to think of this. So all these marbles are really tightly squashed together, and if we start moving, it's like moving a whole wheel. So that's what's happening here, and all these charges are all moved together. So let's see, as they're all moving together, what's going to happen throughout this circuit. Well, they're all moving now, so all of these are moving in this direction. Now, with a diode, the fact of a diode is, you can think of a diode, it's the easiest way to think of it, is charges will only move one way through a diode. I won't go into the reasons why, you don't need to know at this point the actual details, but take it from this, you can think of a diode as being a gate. So charges that are trying to go through this way of that diode can't get through because the symbol here is this gate. So you can think of that as a closed gate, but in the other direction they will let charges through. So think of a diode as a valve. It's a one-way valve, and that's the easiest way to think of it at this level. So you can go through, and here you can see, well, the marbles can't be pushed through there. There's a gate in the way, so they're all moving at the same time at exactly the same instant, so the only way they can go is through this path here, so they're all going to be moving through here. Again, this diode, they can't go through that diode. They're all moving, so they're all moving, and here I've got a resistor here. Now you notice when I'm using this pipe, it's another interesting point about this visualization. The pipes being small, you can see that's like a resistance, and because it's harder to push marbles through a small pipe than it is a wide pipe, so you can see that that's going to use energy. So there's two components here that are using up energy, and it's just these two resistors. So through this whole circuit, so the 36 volts or the 36 joules per coulomb that gets used up when all of these charges flow between the top part of this secondary coil all the way around to the bottom part. In other words, they're all moving together. That amount of energy that gets released is nearly all released by these two resistors. There is a small amount of energy released by these diodes, or the two diodes actually, that are actually in effect during one of these 1/50th of a second. Only two are actually activated during one of these cycles. The next 1/50th of a second, these two will be activated. But yeah, they drop when we talk about using energy. You often hear the term dropping voltage. Well, that's the same thing. When we say drop in voltage, we mean the amount of energy that is being consumed per coulomb that flows through. So by saying a drop of voltage, it's the same thing. When we say there's a drop in voltage from here to here, it's the same as saying a small amount of energy is being used up from going from this point to this point. So these drop a small amount of energy, or drop a small amount of voltage. These two here will use up most of the energy. That's in other words, they will drop the full 36 joules per coulomb. So the 36 joules will be dropped by these two resistors here. Now, of course, in the real circuit, they're capacitors. I'm just using this to show you how the charges flow through a rectifier. So if we just carry on there, we can see here that because they're both offering the same amount of resistance, you can logically see that 36 joules or 36 volts is being divided equally between both of these resistors. Now, of course, half of 36 is 18 volts. So that 18 volts has got nothing to do with the fact that that's 18 kilo ohms. You know, that just happens to be a coincidence. So don't think that that's anything to do with that number 18 there. What's important, that could have been 10 ohms and that could have been 10 ohms. If that was 10 ohms and that was 10 ohms, you'd still be dropping half the voltage across this resistor, because both these resistors are the same value. So you drop half the energy over that one and half over that one because they're the same value. What does that mean to this point here? Well, it means that the potential, the amount of energy that will be dropped from here to here is obviously half. So that is 18 joules per coulomb. So we can call this point 18 volts. Now, of course, that's the same voltage as at the center of this tapping. So that's 18 volts, that's 18 volts, therefore they're at the same potential, so no charges will flow through this center tap. So that's the important point to realize here. The center tap in this particular situation isn't actually doing anything. It could actually, you know, if we could always guarantee that that resistance and that resistor were going to be the same value, absolutely the same value, then we actually wouldn't need this center tap. We could actually, you know, we would actually measure plus 18 on this side, stick our black lead of our multimeter on here, it would be the same potential as here, and if we stuck the red lead down here, we'd measure minus 18 volts. So that would give us our plus and our minus 18 volts. But in reality, of course, these resistors are just representing a bigger circuit. So, you know, this could be moved on to through a capacitor and then through a totally different circuit. The same with this. This would move on to a totally different circuit full of all sorts of different components. And then they're going to be at a different resistance. They're going to offer a different impedance or resistance. And if that's the case, then if this center tap wasn't here, then you wouldn't get 18 volts dropped across. You'd get something completely different. And I'll show you how that works in the next example. Okay, before I talk about what the effect of two different resistors will have, let's just think about the next 1/50th of a second, and that is when the charges at the power station are now going in the other direction. So this time, instead of coming in this way, they're coming in through the top here, they're going down the primary, and remember, they're all moving at the same time. This is like one continuous movement because all of the charges are virtually touching each other, so they're all moving together. So they're all moving in this direction, and what happens is it produces a magnetic field again as before, and it induces the charges on the secondary coil to also move, and this time again in the other direction. So instead of them coming out here now, they're all moving this way round. And remember, they're all moving at the same time. So where are they all moving? Well, they're all moving in this direction, and when we're here, they're not going to move through this diode because they can't, because of this cross. So they're all going to move through this diode. They get through here. Now the easiest path for them to go is to go all the way round, back through here. So that's what they're going to do. They're going to take the path of least resistance, and that's through here because there's only this little bit of resistance here, through there, back through this diode, and back to the other end of where these charges are being pushed through. So you can see it's like a wheel, and it's being turned around, and they're all turning at the same time. Again, the only places that the energy is being used up is a little bit by these two diodes, and mostly by these two resistors. Now, I was talking about those resistors. They just happen to be 18 kilo ohms. They could have been anything. Now, what's the difference if these were 10? If that one was 10 kilo ohms and that one was 10 kilo ohms, you would still have the 18 joules of energy used up from a coulomb. If a coulomb moves between here and here, then 18 joules will be used up. If a coulomb of charge moves from this point to this point, another 18 joules will be used up, irrespective of what size these resistors are. So we know that if we put a smaller resistance here, in other words a wider pipe, then the charges are going to move more quickly. So you can see that with a smaller resistance, what we'll actually have is this coulomb of charge actually arriving more quickly. So that 18 joules will be used up more quickly. So that's the kind of definition of power, really. The faster you use up energy, the larger the power. That's what power actually means. Power is joules per second. So if you increase that rate of usage of energy, you're increasing the power. It means the same thing. So that's really all I wanted to say. All we've really done is gone around the other way. And the thing I want you to notice is that the charges are still going in the same direction. They're still going down this way. So when you look at the original input, which was 339 volts peak to peak, we had an alternating voltage there. Now what we've done is we've dropped it down on this side to 36. So we've got 18 plus on this side and 18 minus on this side. It's always one side of the center here. It's on one side. So in this case, it's all positive. So that's a positive DC voltage. And on the bottom side, you can see it's all negative. So that's a negative DC voltage. There's no alternating voltage anymore. So what we've done with these rectifiers is we've given ourselves a plus 18 volts on this side, Okay, it's a pulsed 18 volts, and we've got a pulsed minus 18 volts on this side. Now later on when we put the capacitors in, that pulsed will be smoothed out and we'll have a ripple voltage. We'll talk about that in a minute. The next thing I'm going to talk about is the condition when we have two slightly different resistances, two slightly different values of resistance, and we'll see what happens then. Okay, it's the same diagram again, but this time I haven't drawn in all of the charges, the marbles. I'm just going to assume you understand like the visualization I was trying to put over there. So all I've done in this one is I've just put the arrows in. So this is the same as the last diagram I showed you, but in this case the only change here is the fact that we've placed different values of resistors here, and now that's going to make clear why the center tap is very useful for a dual supply. Now what we want with a dual supply is we always want to be able to see from this point here to this point here an 18 volt drop. We also want to be able to see from this point here to this point here another 18 volt drop. Now the way we can do that is if we have the center tap here, and if we happen to use a multimeter and put our black lead here and then put our red lead here, we're going to measure 18 volts. That transformer is an 18 to 0 volt transformer, and when charges are moving through the primary, you will measure a voltage drop across this side if you put your red lead there and your black lead there of 18 volts, and if you leave your black lead there, just like in the battery example, and you put your red lead down at the bottom there, you're going to measure, the multimeter is going to say minus 18. What that means is 18 volts is dropped when charges move between this point and this point, and between that point and that point. And it's the same, obviously it's the same in the circuit. As we go through the circuit, then the 18 volts at this point is going to drop down across this resistor. And remember, in this case, the center tap is connected to this point. So this is also always going to be 18 volts above here. Now, this point here is actually, if we follow it through, is this point here. This point and this point, you can see, if you follow it through, they're the same location. So what that means is, no matter what resistor we place here, it's always forced to be 18 volts across it. So what happens here, just to give you an example, if we just think, right, 18 volts is dropping across an 18 kilo ohm resistor, we know that 18 volts are dropping across it because we know that there's an 18 volt drop between here and here. Therefore 18 has to drop across there. So what that means is 18, if we use Ohm's law, we can stick in our 18 for our V here, divide through by our 18 kilo ohms, and what we'll find is 1 milliamp. And we would have found that in the last example. We would have found, in fact, the last example would have been 1 milliamp all the way round. The same amount of current would have flowed all the way round. You can't have a different current in one part of the circuit to another part in the same circuit, only if it splits. Here, we've got a situation where we've got 1 milliamp going through this 8 kilo ohm resistor. We've used Ohm's law to figure it out. Well, we know there's 18 volts here. There has to be, because it's at the center tap. And that is an 18 volt drop. So we know that that's at 18 volts. Now that means that 18 volts must drop across the 5 kilo ohm. So, because we know that that point there is at the bottom of this cable. So we're dropping the full 18 volts across here. So what that means is that the amount of current that's flowing through here is going to be the 18 volts divided by the 5 kilo ohms. It's going to give us 3.6 milliamps. Now, where does the extra... We know that the charge leaving has to be the same as the charge entering. So now we've got 3.6 milliamps. That must imply that we're getting charge from somewhere else, because there's only 1 milliamp flowing through here. Now, of course, what that means is that that's where the center tap actually comes in useful. Because this is an 18 volt drop across here, the difference up to 3.6 is, we will find, is 2.6 milliamps. So what's actually happening, because that's 18 volt drop from there to there, extra current is being drawn through the center tap here to ensure that we get 3.6 milliamps here. Now what that means is that if you do 3.6 milliamps times 5 kiloohms, if you do that on your calculator, 5,000 times 3.6 times 10 to the minus 3, if you do that on your calculator, you'll get 18 volts. So we're still dropping 18 volts. So I hope that maybe that's sounded more confusing than what it is. It's quite hard to describe this in words, but the basic point is that no matter what resistors we put in these two places, because we've got the center tap, it's always forcing an 18 volt drop. We're going to get a different current flowing through here than we are flowing through here, and the shortfall is going to be provided by the center tap. So that is why the center tap is essential in a dual power supply, because if we want to maintain a plus 18 volts and a minus 18 volts, there's always going to be situations where there's a shortfall. And it could be the other way around. We could have the 5 kiloohms here and the 18 kiloohms, and then that situation, what would happen is charge would flow through here, and then the shortfall would actually flow back through the center tap, and the rest of it would flow through here. So you can see no matter what resistance we have on either side of this center tap, we're still going to get plus 18 volts above and minus 18 volts below. Now I've gone through that quite quickly, and you can prove it just by using Ohm's law and simple current laws. You know, current entering is the same as the current leaving, Kirchhoff's laws, if you know those. So these are all very logical really when you think about it, but it does require a bit of thinking. So yeah, so that's how the transformer works. So what we've done here in this example is basically we've used two resistors so that I could show you how the center tap works in this situation. So you can imagine that if we powered up, we could power up a different set of components on this side as we had on this side. It wouldn't matter what it was. It could be a radio on that side, it could be an amplifier on that side. That radio would see a plus 18 volts and that amplifier would see a minus 18 volts, no matter what the impedance was. So that's what we're after. We're after a dual supply that will keep a steady plus and minus 18 volts. So that's the purpose of the dual supply. So we've gone over the sort of the most complicated part of this, the visualization of how the charges move through a rectifier and the center tap. That's probably the hardest thing to understand. Now what we're going to talk about in the next part is how the capacitor works. Now we're just going to talk about the plus side. We're not going to worry about what happens on the plus side. As you can imagine from this discussion, is obviously going to be the same as what happens on the minus side, but in reverse. Yeah. So I'm not going to repeat everything that I discuss on the plus side. I'm just going to make sure that you assume that it's the same. Those resistors in the last diagram have now been replaced with capacitors. We've got something we can do which is a very neat solution. Now remember, if we just go through this, we're going to end up with a pulsating plus 18 volt DC voltage on this side. So we haven't got rid of those pulses, although we've made sure that it's all on the positive side on this side, and down here it's all on the negative side. What we've got is a pulsating voltage. We don't want that. We want as smooth voltage as we can get. So these capacitors are going to go a long way towards smoothing that out. And it's because of the way capacitors work that enable us to use a nice little trick to do that now. So let's think about what's happening here. Now we're going to go for 1/50th of a second again, and we're just going to imagine we've just switched this on. So charges are going to be as always, they're going to be flowing in the same direction. They're always going to be flowing down in this direction for both those cycles actually. So they're always going to be flowing down here. They're going to be flowing through here. Or in fact, they're not flowing through a capacitor actually. What actually happens, as soon as that voltage is on, there's a repulsive force against the ones down here, and they all push each other through this same repulsive force. Same thing happens on the bottom capacitor. This repulsive business only happens for a very, very short period of time. Now, the trick here is to find a capacitor. I'm not going to go through the formulas. There are formulas you can use, mathematical formulas that give you the right size of capacitor for this. It's actually not that complicated, but I don't want to go through it here. We can go through it some other time. But you can easily work out the size of a capacitor to actually work out the size for this time period where the capacitor is charging up. We want to select a capacitor. We know the time period here is 1/50th of a second. So if we can select a capacitor that's going to give us that response over 1/50th of a second, then we can effectively smooth out that pulsed voltage. It won't be completely smoothed out, but it will be almost smoothed out. And how does that happen? Well, first of all, we're going to push charges through here, and then a moment later nothing's going to be going through here because it's swapped polarity. Now, what does that mean? That means for that moment here, you can see it drops down to 0. Now, it would have done if there was a resistor there, but now that it would have dropped down to 0 if there was just a resistor there, because it would have burnt the energy up. But now we've got a capacitor. What actually happens is that energy wasn't burnt up, it's just stored on this plate. Think of the top plate here, all of those charges just been stored, and on the bottom plate a negative space has been stored. So when we're down in this valley from the actual pulsating DC voltage, when we get down here, when there's it drops below the value of this. Now these charges now are at a higher potential than this, and they're at a higher potential than anything that we join from here down to here, or here down to here. If we join something, you know, a circuit from here to here, that's going to be at a higher potential than that. So then we can power a circuit. So what happens is, during this period where we're down in the valley here, these positive charges, they can't go this way because obviously there is 2 diodes there with bars across them, and this potential here is effectively not in the circuit anymore. So where the charge is going to flow? Well, they're going to flow out, and that's when they fill in these valleys here. They get filled in, because if you put a multimeter here, put your red lead of your multimeter here and your black lead here, you're going to see this effect. It's going to drop a little bit, and that's where the ripple voltage is. You know, so you're not going to get a perfect flat line, but you're going to get this almost perfect flat line, and that's what the filter capacitors do. So that's really how that works. So everything else is pretty much explained. It was just this last bit with the capacitors now that you can see what the capacitors are very useful. And so here, for example, this is shown as not being connected to anything, but actually this would be we would be treating this as our common ground, and you could have a piece of equipment joined to this one and using that as a common ground. That would give you a minus supply. This one will be joined to another piece of electrical equipment, and that would your common again. And like I said before, if there was different resistances on that extra circuit, remember that this capacitor and this impedance would add up, but it wouldn't matter because you've got this central tapped common here. You're always going to see this 18-volt drop, and in fact this is nicely smoothed out, so not only are you going to see the 18-volt drop, you're going to see a much smoother version of that 18-volt drop, and the same here, you're going to see a much smoother version of that minus 18-volt drop across here. So that's really what's going on here with these filter capacitors. On to the next stage, which will be the regulator, and then we're going to take this ripple voltage and just regulate it a bit more.